Hey everyone, Mr. Kier here. This video is going to be looking at factors that affect the solubility of solutions. So what I have here is I've got a picture of some rock candy. Why do I have a picture of this rock candy? Well, we're going to be using solubility to explain how it's actually formed. Today you're going to find out why pop fizzes when you open it. And we're also going to find out about this poor goldfish. Why does it look so terrified? What did I do to goldfish in the past? So these are all stories we'll be explaining later in this video. So their factors that affect solubility are threefold. There's the size, temperature, and pressure. We'll be looking at each of these. So when you look at size, small molecules are really tiny, and it's very easy for them to associate with water molecules, and as a result, they're much more soluble. So small molecules are easy to dissolve. Larger ones have a harder time associating with the water molecules, and they have a harder time to dissolve. So think of the size. Now, temperature can also be a factor. You know this already. If you want to dissolve more of something, for example, you might have some tea, or you might have some instant coffee, or some other powder you want to dissolve in water. By heating it up, you make that process happen faster. And what's going on is, but as you're heating up the water, each molecule has a lot more energy. The water molecules have more energy. And because they've got more energy, so say for example, I've got sodium chloride, just as an example, what happens is the water molecules have more kinetic energy, and they can get in here and they can overcome the attractions between the ions much more easily. So the higher the temperature, typically, the better things dissolve. So to look at that, we actually can have something called a solubility curve. So this shows you the maximum amount of that substance that can dissolve at a given temperature. So the maximum amount is called saturated. So the solution can be saturated at that temperature. Let's look at an example. So at 30 degrees, the most sucrose that we can dissolve in water would be 220 grams per 100 milliliters. So it's quite a bit of solubility, right? And what you'll notice is that it changes with temperature. So if I go over to, say, I don't know, like, let's look at 80 degrees here. So at 80 degrees, we can dissolve a lot more. We're looking at about 360 grams that we can dissolve of this sucrose solution. So again, these solubility graphs or curves are really handy to determine how much you can actually dissolve. Now, solution that contains the maximum amount at a given temperature right on this line is said to be saturated. So this would be the saturation line. If you dissolve less than that amount, we say the solution is unsaturated. So for example, if I dissolved 100 grams of sucrose at 20 degrees Celsius, I still have room to dissolve more sucrose. I'm not full, so the solution can still hold more sucrose. So we say it's unsaturated as a result. Now, what can happen is you can dissolve temporarily extra solid at a given temperature, and then that's called a supersaturated solution. The only thing is that eventually you can't sustain that for a longer period of time, and then eventually the extra that you have here that's above the saturation is going to precipitate. I'll look at an example in a little bit. So let's look at this. So if I've got a solution, and let's say I'm dissolving something. I think it's a sodium carbonate or something like that. And what happens here is that you can keep adding and adding and adding and adding the solute until you hit this line here. This will be the maximum amount that you can dissolve. So in the case of the substance, it's 91 degrees. So if I tried dissolving 100 grams of the solid, only 91 grams can dissolve. The rest stays at the bottom. But what can we do to dissolve the rest? We can heat up the sample. So if you heat it up a little bit, you can dissolve this extra little bit here. So you see this, it's soluble at a higher temperature. If you dissolve this, and you slowly cool the solution. And when you slowly cool it, what's going to happen is the extra solute that you have is going to gradually precipitate out over time. And that's what happens here. So after you cool the solution here, Later on, you can again only hold 91 grams, and that extra 9 grams precipitates out. And that's the idea behind rock candy. So in rock candy, it's going to show us a very quick clip here, parts of it, not the whole thing. So this rock candy that we have, so I'm just going to get a mouse over here. Okay, it's formed like this. You take a bunch of glucose, sucrose, sugar, and you heat it. And this is going to make a supersaturated solution. So this supersaturated solution, remember, it's only temporary. You have a lot of extra solid in here that normally can't be in there. So eventually it's going to settle out. We take advantage of that by putting a piece of string in, and the sugar will start to precipitate, not at the bottom, but on the string instead. Let's see what happens. Oh, let me go a little bit more. And you can see here that all of that extra that we dissolved, the extra sucrose, is now precipitated out. So this solution in here is saturated. Okay, it was super saturated, now it's just saturated, and the extra fell out. So something to keep in mind. So there's a couple of questions we can give you. For example, what mass of sucrose can dissolve in 100 grams of water at 60 degrees Celsius? Just go up here, and then you go across, and you just read off of the graph. It's that easy. What temperature does 350 degrees of sucrose become saturated? So you go over here, and just go across. Oh, my saturation would be right there. So at this point, 350 grams solution would be saturated, 77 degrees. How about this? What if I had a saturated solution at 65 and it's allowed to cool to 30 degrees? This is kind of like our rock candy example. Here we go. We're at 65 degrees, and then we cool it down to 30 degrees. I can't hold as much. So at 30 degrees, I can only hold 220 grams. At 65 degrees, I can hold about, I don't know, maybe 310 grams. So what happens is this extra little bit that we dissolved will gradually precipitate out. So this extra piece here, or the extra bit of sugar, will precipitate out to the bottom. I can't hold all that sugar. It's only temporary. Remember, so supersaturated solutions are temporary. The extra that's dissolved in there will eventually precipitate to the bottom. Okay, there we go. Now, usually when we look at solubility curves, you have a lot of different compounds on one graph. It's not just one. Just focus on one. So I could ask you, what is the solubility of potassium chloride at 50 degrees? So just all you do, 50 degrees, go up to potassium chloride. How much can we dissolve? Around 42 grams. So they look confusing, but they're really, really easy to use in effect. All right, how about this poor goldfish? Well, I'll tell you about this goldfish, but it involves a light. So what happens is when you take gases and you heat or cool them, you change the solubility of those gases. So this teacher is going to show you 3 different soda bottles. These are just filled with soda water, just carbon dioxide, no sugar. And he's going to open them after placing one in ice, one in a hot water bath, and one at room temperature. Oh, that was the room temperature water. So this is the cold water. And most of the gas stayed inside. And that is the hot one. So you can see here that all the gas that was inside is leaving. So we had all this trapped carbon dioxide put under pressure in the bottle, and when you heat it up, look how much of it left. So what this means is that as the temperature goes up, the solubility of gases goes down. So solubility of gases go down. Why is that? Well, at higher temperature, what's happening here is that the water molecules at high temperature have enough energy to overcome the attraction between all the other water molecules here. Same is true for this for the solid, the carbon dioxide. It's attracted to these other molecules of water and itself, and basically it doesn't want to leave, but if it has enough energy, if it's high temperature, a lot of these solid molecules can actually leave. So in this case, it was carbon dioxide. At lower temperatures, there's a lot of attraction still between these molecules with each other and the water, and therefore the CO2 or whatever other solid it is doesn't have a lot of energy and can't really pull away from that interaction. So why is that important for my fish? Well, let me just look at this, for example. Yeah, there you can see all the water, the solid molecules leaving. What happened with my poor fish was this. Oh, sorry, let me go. So I had a fish tank, and there's my fish inside here, all very happy. And then I had oxygen dissolved in here. There's a little bubble. I guess it has enough oxygen for it to survive. I put a or a very bright lamp on top of here, thinking it would be great for the fish because it's a very, very dark environment. This is obviously, I was very young. The lamp heated up the water. And remember, you heat up the water, the oxygen molecules have lots of extra energy, so now they can leave the attractive forces between themselves and the water molecules. So all the oxygen left. And what happened with my poor fish? It was upside down the next day. Oh, it was a very sad story, but I learned from that, okay? So I'm never going to do that again. And this would be the solubility of oxygen or any other gas. So it's really important. It's opposite trends. Remember, the solids, the trend is as you increase temperature, solubility goes up. For gases, though, it's the opposite. As you increase the temperature, less of the gas can be dissolved inside there. Oh, and that's why when it comes to summer days, the fish like to be at the cooler bottom part of the pond or lake. They don't like to be near the top because there's very low oxygen in hot water. All right, how about this? Why does my pop can fizz? Well, what happens is it's all because of pressure. So what you can do is you can pressurize different substances. Now, pressure has no effect on the solubility of solids or liquids because the particles are so close to each other. However, for gases, it plays a huge role. So you can compress gases very easily. Look at all these gas particles getting closer and closer together. So what happens is if you have carbonated beverage, you can put a lot of extra CO2 into a pop bottle simply by pushing it in there with very, very high pressure. So as the pressure goes up, the solubility of gases increases as well. Now, when you release all that pressure, so you take the cap off, there's less pressure pushing on the carbon dioxide, and that's where this fizziness happens. It's reduced. There's less pressure and the gas is less soluble, so it leaves the water. So simple as that. And you can see here how you increase pressure, you increase the solubility of gases. So that's it. So hopefully you have an appreciation for solubility and how it might impact things in your everyday life. Take care.